Hi, welcome to Webinar 6. This is all about Unit 3, the first part about Unit 3, Intermolecular Forces. So how molecules are attracted to each other, and then how do you separate those molecules based on those intermolecular forces. Intermolecular forces are different from intramolecular forces. Inter means between. Intra means within. So we're talking about not a covalent bond between hydrogen and oxygen and water. We're talking about the bond between one water molecule and another water molecule. So these are the forces you've probably heard back in the day, like LDF or hydrogen bonds. So the dotted line on the left, this is an intermolecular attraction. So that's a force of attraction, and that's governed by Coulomb's law. Coulomb's law says that the force of attraction is due to the amount of charge and also to the distance between them. The black bond over on the right is an example of a covalent bond, an intramolecular attraction. Intermolecular forces affect all the properties of substances. So when do they boil? When do they melt? How do they respond when you step on them? So if you've ever been walking down the road and you've been on a sidewalk and you notice a big rubber pad at the end of a sidewalk and it's got bumps on it, that pad is made out of a special kind of plastic that was designed to have certain intermolecular forces. Those intermolecular forces are very important because if they're too weak, then in the hot summer, it would melt. If it was too strong, then in the cold winter, they would actually get so hard and brittle that when you stepped on them, they could break apart. So you want it not too hard, not too soft. You want those intermolecular forces to be just right. The types of intermolecular forces that you've been taught over the years, London dispersion forces, and we'll go over each one, dipole-dipole forces. And just to remind you, a dipole is when something has two poles, has a positive end and a negative end. So a molecule that has dipole-dipole forces is one in which it's polar, has a positive and negative end, and it's attracted to another molecule that's polar. And there are a couple subsets of these that we want to talk about later. Just realize that dipole-dipole forces are a very general type of force of attraction between molecules. Hydrogen bonding isn't really a bond so much as it's a hydrogen, so much as it's a force of attraction that's stronger than the typical dipole-dipole force. And then you've got ion dipole, and those are pretty simple. So let's jump in and see what we can see. All molecules that have electrons have LDFs, or London dispersion forces. Nonpolar things. So we've done Lewis structures, and we've looked at Lewis structures and decided were the electrons evenly distributed, or were the electrons more so to one side of the molecule than the other. When they're evenly distributed, we call that a nonpolar molecule. The best example of nonpolar molecules are the halogens, F2, Cl2, Br2, and I2, where one thing is not pulling on the electrons more than the other. They have the same electronegativity. The other nonpolar molecules that we want to look out for are the hydrocarbons. So CH4, things with just carbon and hydrogen, C2H6, C3H8, things like that. So down here we have two molecules, a neon and a neon, and their electrons are very evenly distributed. But remember that the electrons are always moving. So imagine a place where for a brief moment, the electrons end up more so on one side of the neon than the other. When the electrons moving around end up on one side more than the other, we call this a dipole moment. This is an instantaneous dipole because they're very short-lived. For a brief moment, the electrons end up on one side versus the other. When you get that molecule on top close to the molecule on the bottom, the electrons on the bottom neon are attracted to the partial positive charge on the other neon. And for a brief moment, one atom that is polar can induce, which means makes, the other molecule polar as well. And since they're both slightly polar, then we would say that this is an instantaneous dipole force, or an LDF. it's very, very weak. But if you have a lot of very, very weak LDFs, they can be quite strong. So how do you decide who has more London dispersion forces? If everyone who has electrons is going to experience LDFs, are some molecules going to have more LDFs than others? Basically, whoever has the greatest number of electrons is more polarizable, meaning there's a greater chance that there's going to be a dipole moment. So imagine a teacher with 4 students and imagine a teacher with 40 students. Which class is the teacher going to tend to be able to keep organized and going on task, and where they won't have a brief moment where one side of the room is doing something different from the other side of the room? Much more likely. So if you have more electrons, you're going to have more LDFs simply because you're more polarizable. And no, I didn't make that word up. In a lot of molecules that only have LDFs, they can have a lot stronger intermolecular forces than even hydrogen bonds. So when we say that hydrogen bonds are stronger, and they're always stronger, that's not necessarily true. A dipole-dipole force is a force of attraction between 2 polar molecules. We already said that, right? So you have 2 molecules that are polar. The electrons are more so on one side of the molecule than the other. The greater the degree of polarity, the stronger the attraction. And that goes back to Coulomb's law. The greater the charge, the stronger the attraction. This is one example of a dipole-dipole force. The hydrogen has a partial positive charge. The chlorine has a partial negative charge. And so the negative side of one molecule will be attracted to the positive side of the other molecule, and we call that a dipole-dipole force. So what's a hydrogen bond then? A hydrogen bond is a dipole-dipole force, so 2 polar molecules, but aren't just polar, they're like crazy polar. So you got regular dipole-dipole, and then you got crazy strong dipole-dipole, and we invented a new term for that, and we called that hydrogen bonding. So who is going to be super polar? The things that are going to be super polar are going to be things that have F over N, because F over N on the periodic table are the most electronegative elements up there. Their electrons are very close to the nucleus, and they have a lot of protons on their row. So they tend to be very electronegative. So when you have a dipole-dipole force that's super, super polar because of F over N, then we call that a hydrogen bond. But notice that it's not enough to just have hydrogen on one side and F over N on the other. In order to be a hydrogen bond, you have to have an oxygen, fluorine, or nitrogen at one side of the molecule, and it has to be attracted to a hydrogen that's also bonded to an F over N on the other molecule. So make sure you know that definition. Very, very important. Here's some examples of hydrogen bonding. You've got a hydrogen stuck to an oxygen. That makes for a very, very polar bond attracted to a fluorine. That's a hydrogen bond. On the second molecule in blue, you've got a hydrogen stuck to a nitrogen. Also a very polar bond, and that's being attracted to an oxygen on another molecule. Over to the right, you see some water molecules. Water molecules is probably your best example of these super, super dipole forces where the H on one molecule is attracted to the oxygen on another. One of the other forces, and this one you may not have ever heard of before, but it makes total sense, is between a polar molecule and an ion. Well, why don't we just call an ion molecule a polar molecule? Why don't we call that a dipole-dipole? Because an ion doesn't have a dipole. It doesn't have a positive end and a negative end. So an ion is just a charged particle, right? It could be an anion, a negative one, or a cation, a positive one. But it's when a dipole force exists between some polar molecule and the ion. And if you've ever dissolved salt in water, been to the beach and tasted salt water, that salt water is basically got these sodium ions floating around, and the water molecules form a sphere around it where the negative side of the water is attracted to the positive side of the sodium. So in this molecule, what kind of attraction would you see? Well, you have a calcium ion, and those little Mickey Mouse faces are exactly like water. So if that's water and calcium, then the only type of force this could be would be ion dipole, because it's an ion and a dipole. So which one of these ions would have the greatest attraction for water? And which one would have the least attraction for water? Well, remember, Coulomb's law says that the biggest charge has the greatest force of attraction. So indium 3+ down here, this would have a very strong force of attraction with water. So which one would have the weakest force of attraction with water? Well, you've got lithium and sodium. They both have a +1 charge. So in terms of charge, they're tied. So between lithium and sodium, which one would have a weaker force of attraction? Well, remember, Coulomb's law talks about charge and distance. So whoever has the greatest distance between it and the water molecule would have the least amount of attraction for the water molecule. Because remember, Coulomb's law, the closer you are, the stronger the force of attraction. The farther away you are, the weaker the force of attraction. So the weakest one up here would be the sodium ion because it's got the smallest charge and the greatest radius. You also hear about a couple of other ones just to kind of cover them. What happens if you have a polar molecule and a non-polar molecule? Well, the polar molecule has a dipole. And when it gets close to a non-polar molecule, then the electrons on the non-polar molecule are going to be really attracted to the polar molecule. So something that is polar can induce or make another molecule polar. So if you get a charged thing next to a non-polar thing, you can actually force that thing to be polar. And if you want to try this at home, you could totally do this. Take a balloon, rub it on your hair, and give it a lot of charge so it'll have a negative charge, and then go hold that next to a stream of water at the sink, or hold it next to somebody else's hair. And what you'll see is you'll see the negative charge on the balloon affect the hair. It will induce the electrons on the hair of the other person to kind of run to the other side, and it'll cause a force of attraction. And then you can also have an ion-induced dipole, where an ion, something that has a charge, gets close to a nonpolar molecule and forces it to be polar. So here's some examples of all those things. Upper left, an ion dipole. The hydrogen bond, the one we always want to say is the strongest, but remember, sometimes LDFs can be stronger. You've got a dipole-dipole force, ion-induced dipole, a dipole-induced dipole, and dispersion. But realize all of them are a force of attraction between a positive charge on one thing and a negative charge on something else. And you get that brief force of attraction. And remember, this is never about inside of a molecule. This is only between two molecules, intermolecular. Now, what does that do? Well, it changes the boiling points. So things with a really strong intermolecular forces have really high boiling points. It takes a lot of energy to break those suckers apart. Things with very, very few intermolecular forces, they tend to have very, very low boiling points. Vapor pressure also relates, and we'll talk about that a little bit more in gases in the coming weeks, but vapor pressure is basically how much of it evaporates. So how much of a given substance turns to vapor. So water has a relatively low vapor pressure, whereas rock has no vapor pressure whatsoever because rock doesn't go into the air. It stays as a solid. That's because those forces holding the rock together super strong, right? Ionic bonds through and through. It's never going to sit there and just start to evaporate. For that reason, things like methane, CH4, has a very low boiling point. In fact, you have to get it crazy, crazy cold before it even forms a liquid and then a solid. Whenever we're boiling or melting something, we're breaking those intermolecular forces, not the covalent bonds. So next time you go in the shower, realize when the water hits your body, it doesn't split into hydrogen and oxygen, because that would be weird. You're not breaking the covalent bonds inside, you're breaking those bonds between the molecules. Next time you make some noodles of some kind, boil that water up. You're not making a cloud of hydrogen and oxygen. Good thing, because that's explosive. Instead, you're breaking the intermolecular forces. So here's some examples of actual melting and boiling points based on the substance. So we've got ionic stuff like lithium fluoride. It's got a crazy high boiling point, melting point. You could not melt lithium fluoride on your stove. It just doesn't get hot enough. You've got metallic bonds, like just straight up beryllium. We talked about those a couple times before. Also a very high melting point. And covalent bonds, like in diamond, all covalent bonds all the time, those also have a very high melting point. But then if you look at the intermolecular forces, if you notice, the stronger the force of attraction, and in general, hydrogen bonds are stronger than London dispersion forces, and hydrogen bonds are stronger than dipole-dipole forces, you'll notice the stronger the force of attraction, the higher the melting and boiling point. Although there are some exceptions to that. So look at these three molecules. Who's going to have the lowest boiling point? Well, the lowest boiling point is going to have the least amount of intermolecular forces. So what type of intermolecular forces would each substance have? So let's look at butanol, the first one. There is a hydrogen, there's lots of hydrogens, but can it hydrogen bond? No, the hydrogen is stuck to a carbon. So remember that in a hydrogen bond, the hydrogen has to be stuck to F, O, or N. Has to be F, O, or N. So there's no hydrogen bonding there. However, the oxygen on butanol, sticking out there, is more electronegative than the carbon. So what's going to happen in this butanol molecule is you're going to have a little bit of negative charge on the oxygen and a little bit of positive charge on the carbon. So you could have a dipole-dipole force between one butanol molecule and another. And it would also have LDFs. Pentane, though, has nothing but carbons and hydrogens. And remember, that's a classic nonpolar molecule. So for a nonpolar molecule, you're only going to have London dispersion forces. Propanoic acid down below, it does have a hydrogen stuck to F, O, or N, O in this case. So it does look like this molecule of propanoic acid could hydrogen bond to the oxygen on another propanoic acid. And that would be quite strong. Propanoic acid is also going to have some dipole-dipole forces, because notice it still has that double bonded oxygen, and that's going to create a dipole force. And it also has LDFs, because remember, anybody that has electrons, they have London dispersion forces. So why show us the molar mass? Well, the molar mass is some indication to us that does something have more electrons than something else. Usually the greater the molar mass, the greater the number of electrons. So since all the molar masses are about the same, then we're not worried about London dispersion forces. So which one is going to have the lowest boiling point? It's going to be the one with the weakest forces, and that would be pentane, because it can only form dispersion forces. If you went and grabbed some halogens, bromine is a liquid, and iodine is a solid, so you can actually buy purple iodine crystals. I2 is a solid, meaning it doesn't melt at 25 degrees, whereas bromine has already melted. That's why it's a liquid. So bromine has a much lower melting point than iodine does. So why is that true? Well, both iodine and bromine are non-polar. So if they're both non-polar, then we're only talking about London dispersion forces. If we look at answer choice D, we see that is the correct answer, because iodine has a stronger set of intermolecular forces because it has more London dispersion forces, because it has more electrons and is thus more polarizable. Answer C looks good because it does say London dispersion forces, but it says they're stronger in bromine than in iodine. And we know that's not true. because bromine already melted and iodine didn't, even though they're both at 25 degrees. So if it were stronger in bromine, then we would expect the bromine to have a higher boiling point. And just because Br is more electronegative has nothing to do with the number of London dispersion forces. Here's 3 molecules. Notice again that each one of the molar masses is about the same. So out of these 3, which one is going to have the highest boiling point? So you can look and go, okay, I'm going to start with butane because that's the easiest one. Butane is just carbons and hydrogens. That only has LDFs. Propanol, that one in the middle, it has an oxygen on one end. Ooh, and look, it's got a hydrogen stuck to it. And whenever a hydrogen is bound to an oxygen, nitrogen, or fluorine, it can be attracted to an F over N on another molecule. So propanol is going to set up a hydrogen bond here. Acetone up top, notice still 3 carbons, same number of hydrogens and same number of oxygens. It's just rearranged. And for acetone up here, notice still 3 carbons, still a bunch of hydrogens and 1 oxygen. It's just been rearranged. Yes, it does have hydrogen, but it cannot make a hydrogen bond. The oxygen on the carbon is going to force that molecule right there to be trigonal planar. So remember, we have to know geometries. And then since the oxygen pulls harder on the electrons because it's more electronegative, the oxygen's going to be a little bit negative and the carbon's going to be a little bit positive. That's going to create a dipole moment. And since it is a dipole moment, when one acetone gets close to the other, you get a dipole force. So the one with the lowest boiling point is going to be butane, and then the next higher boiling point will be acetone because it only does dipole-dipole. And then you've got one propanol coming in with the highest boiling point because it's got the strongest intermolecular forces, those hydrogen bonds. When you mix something into a liquid, for usually that means water, right? So when you dissolve Kool-Aid, sugar, salt, anything like that, we think about polar things like to dissolve other polar things, and non-polar things dissolve other non-polar things. So if you want to dissolve grease, use a non-polar solvent, not water. So why does that occur? And the answer is intermolecular forces. The answer is always intermolecular forces. Is ethanol soluble in water? Well, if you were to draw out the Lewis structure, the OH group on the end causes the molecule to be polar. So yes, that thing will, since it's polar, want to dissolve in water because water is also polar. What about CH4? No. Remember, CH4 is non-polar. Any hydrocarbon like that, just carbons and hydrogens, is going to tend to be non-polar. So it's not going to be crazy about mixing together. The only force of attraction it would tend to have would be LDFs, which is not strong enough to pull the CH4 molecules apart from each other and make them intersperse in the water. So how can we use this to our advantage? We can take a mixture of things. So take Kool-Aid, purple Kool-Aid. How do you make purple? Red and blue. So if you were to take purple Kool-Aid, how do you separate out the red dye from the blue dye? And one technique for that is chromatography. So we're going to take a piece of paper called chromatography paper. We're going to put some ink or Kool-Aid on it, and then you put that in the solvent. Now, you can use whatever solvent you want. You can use a non-polar or polar solvent. But remember, whether or not something is polar will definitely affect whether something will be soluble. So you really have 2 things going on. First of all, how strongly attracted is the dye to the paper, and how strongly attracted to the dye is the solvent. All those things are going to tell us whether how fast something is going to move up that strip of paper. So here is a chromatograph, right? So on the left, we took a piece of paper, we put a drop of ink, could have been Kool-Aid, and we dipped the whole thing in water. And as the water went up, 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 it separated the components into a blue, a purple, and a yellow dye. And so we call this liquid chromatography because you're actually using a liquid moving up the paper. Some molecules are going to be more soluble in the water and will travel faster along with it, and some things will travel more slowly. So which one went the fastest? The blue one. That makes it probably the most polar. Which one really liked the paper? Or on the other hand, which one didn't like the water? The yellow one. So here's a sample question. If you dipped them both in water and they moved up, 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 then which dye is the most polar? Is it C, A, or B? Well, you might think it's C, but before we think it's C, let's ask ourselves this very important question. Notice that the solvent front at the very, very top is not the same distance. So the solvent went farther in the piece of paper on the left and not as far in the piece of paper on the right. So we have to calculate something called an RF. And the RF tells us the retention factor. So the distance traveled by the part divided by the distance traveled by the solvent. So for A right here, if you look, it looks like it went about halfway. If we look at the unknown spot on the right, it also looks like it went about halfway. So that would be a retention factor of about 0.5. So when you compare the two, look for the solvent fronts being the same. But out of all those things, which one seemed to be the most polar, really, really liked the water the most, and went up, 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 and that would be dye C. So we can use liquid chromatography. There's also one called gas chromatography, and we use that to sniff the air. They can use that to find explosives in the air. They can also use that to find what are the flavor molecules in a lot of the foods that we eat. So to separate them out, we can use chromatography or we can use distillation. Distillation is just a mixture in one flask, shown here in red, and we heat it up. And since the molecules are going to have slightly different intermolecular forces, they're going to have slightly different boiling points. And so as they boil off, they go up in the flask, and then they go down in this thing called a condenser, and the condenser cools them down and forces them to be a liquid. So by heating them up slowly, all the molecules with the least amount of intermolecular forces will boil away first, and they'll land in the distillate, and then you move that beaker out of the way, and then you heat it up some more, and as the boiling point increases, now molecules with more intermolecular forces will boil away, and they will condense, and you can catch them. So by moving that distillate away, so you collect one sample and then a second sample and a third sample, it's just a way of collecting all the different parts that made up that red solution. So let's take a mixture of nonane and 2,3,4-trifluoropentane. You don't have to know what that is. But if we put them in a flask together and started heating them up, which one would boil away first and which one would be the last one to boil? The 2,3,4-trifluoropentane, because it's got the lowest boiling point. And then the nonane would boil away last because it's got the higher boiling point. So what should be the last liquid in the flask? And that should be nonane, because the nonane has the highest boiling point. So it won't boil away. Now, let's think about intermolecular forces for a minute, though. What could cause nonane to have a higher boiling point? I know you want to say hydrogen bond, but you can't always say hydrogen bond. So look at the molar mass. What do you notice about the molar mass? It's about the same. That means that they both have LDFs going on, right? And then you've got the 2,3,4-trifluoropentane. That's got fluorine in it. Fluorine tends to make polar molecules. So if you have fluorine on it, you might think, oh man, fluorine, it's definitely going to win. That sucker's got way more intermolecular forces, dipole, all over the place. 2,3-trifluoropentane for the win. But look at the boiling point. It's much lower. So when you're faced with evidence like this, and you're like, wait, I thought fluorine always won. Remember, LDFs can win sometimes. So if you look at nonane, it has a higher boiling point and it's nonpolar. So what's going on? It must just be that it has more LDFs and that those LDFs are stronger than the LDFs and the dipole-dipole forces of the 2,3,4 trifluoropentane. You don't have to know that just by looking at it. You just have to be able to look at the data and ask, what is the data telling me? So we'll end on this one. Normally, chlorine has a boiling point of 238 Kelvin, and hydrogen chloride has a boiling point of 188 Kelvin. Now, why is there the difference? And notice that the question says account for the difference based on the types of intermolecular forces in the substances. Discuss both of them. Well, Cl2 is nonpolar. And since it's nonpolar, it will only have LDFs. HCl is definitely polar. In fact, HCl was one of the molecules that we did at the very beginning, and it was a good example of a dipole-dipole force. And we always say, yeah, LDFs don't matter, but look at the data. According to the data, who has the higher boiling point? Cl2. And if chlorine has the higher boiling point, that must mean it has the greatest amount of intermolecular forces. So we would say that the chlorine has more LDFs because it has more electrons and is thus more polarizable. And this greater amount of intermolecular forces of chlorine means it has a higher boiling point, even though HCl has dipole-dipole forces and LDF forces. So hopefully that gets you back on the path of thinking about and working through intermolecular forces. Next week, we'll work on, okay, what about gases? What about changes of state? And what about making solutions some more? Until next week, have a great day, and we'll see you next week at 1 p.m.